So today we're going to talk about linear and angular velocity, but before we do that, we want to talk about arc length because we're going to be using that in the problems. So recall that the arc length can be calculated by considering an arc as a fraction of the entire circle. So here's the entire circle all the way around, and this is our arc length in red, which we're going to label as L for arc length. So the arc length L over the whole, which is 2 pi r, the circumference, is equal to the angle theta over the whole, which is 360. So multiply both sides by 2 pi r, so you get theta times 2 pi r over 360 is equal to, and when we simplify, theta pi r over 180, where theta is in degrees. So remember that when we're taking a degree measure and we're changing to radians, we multiply by pi over 180. So if we actually get rid of this pi over 180, we're left with our arc length is equal to our radius times theta. And so we're going to be using radians more than degrees when we're doing these problems. So just always assume you're in radians unless it specifically tells you to use degrees. So that's where this formula comes from. So let's go ahead and now look at or talk about angular and linear velocity. So suppose a wheel is rotating at a constant rate around its center, O, and P is a point on the outer edge of the wheel. There are two ways to measure the speed of point P in terms of the distance traveled, which is the linear velocity, so we can measure it in terms of the total distance that we're traveling here. And we also call linear velocity the linear speed. So again, it measures how quickly an object moves on the edge of the wheel. Or we can measure in terms of the angular velocity. So the angular velocity, which is also called the angular speed, measures how quickly the angle is turning. So we're measuring how quickly is this angle actually turning. Another thing we want to recall is that, remember, the radius is equal to 1 radian measure. So don't forget about distance being equal to rate times time. So when we're talking about the velocity, we're talking about the speed, which is your rate. So if we solve for the rate, we actually get the distance over time. So the linear speed is going to be equal to the distance divided by the time. Well, what is that distance? If we're talking about this outer edge of the wheel, we're talking about the arc length over time. So remember, we said the arc length is r times theta over t. So we're going to be using that equation for our linear speed. Now, linear speed, normally you'll see things such as like feet per minute, maybe miles per hour, because it's always going to be some distance per time. So you guys have been working with that a lot in the past. We're also going to be looking at the angular speed, which is going to be the angle versus time. So for the angular speed, you're going to see things such as radians, maybe per minutes, or revolutions per second, some angle versus time. That's what tells you it's the angular speed. So for linear speed, I'm going to label it LS instead of using the V, and angular speed I'm going to label as AS. Notice the two formulas are very similar, so the only difference is that we have added the R here. So we could also say that the linear speed is equal to the radius times the angular speed, because sometimes that'll help you solve some of these problems. So let's go ahead and take a look at this first example. So the second hand on a clock is 6 inches long. How far does the tip of the second hand move in 15 seconds? So for this, we're talking about how far we're moving in 15 seconds, which would be a linear speed. So for our linear speed, we know that's equal to the arc length over the time, so distance over time. So that means we have r theta over t. So we need to, first, we know what our r is equal to because it says the second hand on the clock is 6 inches long. So r is equal to 6 inches. But we don't know what theta is equal to, so we have to figure that out. So let's think about it as a part of the whole. So theta is equal to 15 seconds out of the whole, which would be 60 seconds. So if we reduce this, we would get 1/4. So 15 seconds is a fourth of the circle. So that's in revolutions. And we actually need to turn this into radians. So if I turn this into radians, remember that you want to multiply it by the whole, which is 2 pi radians. So 2 pi radians per 1 revolution would actually give me pi over 2 radians. And we also knew that anyway, because a fourth of a circle, think about 90 degrees, pi over 2, so that makes sense. So now that I have my r and I have my theta, and I know my time, which is 15 seconds, I can go ahead and set this into my equation. So we have 6 for my r, so 6 inches. And remember, inches, the radius is always per 1 radian, so I'm always going to write the radius over 1 radian. So 6 inches per 1 radian times, and we have our angle, which is pi over 2 radians. And the reason I like having that is because then notice that your radians cancel out. And that's all over because it's your arc length versus time. So my time is 15 seconds. So when we simplify this, 6 times pi over 2 is actually 3 pi, and notice we're only left with inches. So 3 pi inches per 15 seconds. And that makes sense because we're talking about a linear speed. So we have a distance versus a time, so inches per seconds. So this right here is actually my solution. So to write it all out, the tip of the second hand moves 3 pi inches in 15 seconds. So that would answer our question. So let's go to the next one. So for the next problem, it says a child is pushing a merry-go-round and makes 8 revolutions, which is rotations per minute. So since we're talking about an angle versus time, this is actually your angular speed. So then it's asking, what is the angular speed of the merry-go-round? Anytime you see that, notice that this is revolutions per minute. Whenever you're using these problems, you always want it in terms of radians. So that means that the first question is actually asking you to put this in terms of radians per minute. So right now we have the angular speed is equal to 8 revolutions per minute. And we're converting this into radians. So remember that's 2 pi radians is equal to 1 revolution. And the reason I put the revolutions on the bottom is because I want them to cancel out. So I'm left with radians per minute. So then this would be equal to 8 times 2 pi. So 16 pi radians per minute would be the new angular speed in terms of radians. And again, when you're doing these, always leave your answers in terms of pi for now. So then for B, the next question says, what is the linear speed of a child sitting 12 feet from the center of the merry-go-round? So the 12 feet from the center means that is going to be our radius. So remember that the linear speed is equal to our arc length, our theta over time. And remember that theta over time is really just your angular speed, which we just did. So really we have r times our angular speed. So we know our angular speed, we just did is 16 pi radians per minute. So we need to then multiply this by our radius, which is 12 feet from the center. So we get our radius 12 feet per 1 radian. Remember, you always want to do your radius per 1 radian times 16 pi radians per minute. And notice that reason we did that is because our radians are going to end up canceling out. And that gives us 12 times 16 pi, which is 192 pi feet per minute. And that would be my linear speed of the child sitting 12 feet from the center. So then for C, it says, what is the linear speed of a child sitting 4 feet from the center? So it's essentially the same. The only difference is that we're changing this portion right here. Instead of being 12 feet, we're going to use the 4 feet. So we have the linear speed is equal to 4 feet per 1 radian times 16 pi radians per minute, which gives us 4 times 16 pi. So 4 times 16 pi gives me 64 pi feet per minute. All right, so the next problem says find the central angle measure in radians of an arc with a length of 11 centimeters on a circle with a radius of 4 centimeters. So for this, again, it says we have an arc of 11 centimeters. So it's this outside part. And a radius of 4 centimeters. And we want to find the central angle measure, which is theta, in coercive terms of radians. So notice this is not saying anything per time, so we're actually not using linear velocity or angular velocity, we're just using our arc length formula. So arc length is equal to r times theta. So our arc length is 11 is equal to r, which is 4 times theta. So all we have to do is solve. So 11 over 4 radians, because we're always using radians when we're using that formula. So this is my answer. So that one's pretty easy. For the next one, this says, as shown below, a small pulley with a radius of 4 centimeters and a large pulley with a radius of 6 centimeters are connected by a belt. The small pulley is turning at 80 revolutions per minute. So the first question says, what is the angular speed of the small pulley in radians? So let's go ahead and highlight some of the things that we do know. So the small pulley has a radius of 4 centimeters. The large pulley radius is 6 centimeters, and it tells us that they're connected by a belt. So if they are connected by a belt, that means that the outside speed that they are moving is going to be the same. So that means that the linear speed is the same for both pulleys. Now it tells us the small pulley is turning at 80 revolutions per minute. So revolutions is an angle per time. So that's your angular speed. So for A, it says what is the angular speed of the small pulley in radians per minute in radians per second. So the angular speed we already have, which is revolutions, so 80 revolutions per minute. But we want to convert it into radians per minute. So if it's not in terms of radians, you should always convert it anyway. So this is 2 pi radians per 1 revolution, because that cancels out my revolutions. So when I do that, I get 160 pi radians per minute. So that would be radians per minute. So that's one answer. Then we want to put this in terms of radians per second. So I'm actually going to multiply this. I have to figure out that there is 60 seconds in 1 minute. So 1 minute would go on top and 60 seconds on the bottom, because that's going to cancel out this minute with this one here. So when I do that, 160 over 60 is going to give me 8/3, and don't forget that pi. So that would be 8 pi radians per 3 seconds. If you wanted to figure out per 1 second, you could just divide the 8 pi over 3, or 8 divided by 3. Now, the second question, B, says what is the linear speed of the rim of the small pulley in centimeters per minute of the larger pulley in centimeters per minute? So remember, because they're connected by this belt, that means this pulley and this pulley are going to have the same linear speed. It's not going to change. So let's go ahead and look at B. So the linear speed, recall, is equal to the arc length. So that's r times theta over time. So remember, linear speed is really equal to the radius times the angular speed. So we just found what the angular speed was per minute right here, 160 pi radians per minute. So we're going to use that one because we want it per minute. So the linear speed is equal to, so this is going to be for the small and the large pulley. So linear speed is equal to, and we said that the radius is 4 centimeters. So the linear speed equals 4 centimeters. So that's the radius, so over 1 radian, times 160 pi radians per 1 minute. And then we're going to cancel out our radians. So when I multiply this out, I get 640 pi centimeters per minute. So as I just said, again, the small and large pulley have the same linear speed because they're connected by the same belt, thus that the distance traveled is going to be the same. So the angular distance, which is the angle in which they're turning, so the rate here and here, because this wheel is bigger, is going to be turning at a different rate than the smaller wheel here. So then the next question says, what is the angular speed of the large pulley in radians per minute? So now we need to find the angular speed of the large pulley. So recall that the angular speed is going to be, we have to figure out what it's equal to. We know it's the angle versus time. So we can also use the fact that we know the linear speed equals the radius times the angular speed. So really, if I do the linear speed divided by the radius, that'll give me my angular speed. So angular speed equals the linear speed divided by the radius. So I'm going to use that in order to help me figure out the angular speed of the large pulley. So the angular speed is equal to, we said that the linear speed was 640 pi centimeters per minute. If we divide that by the radius, if I go back up here, the radius of the large pulley was 6 centimeters. So we're going to use that. So divided by 6 centimeters. Remember, your radius is always over 1 radian. So now we're dividing these two fractions. So 640 pi centimeters per minute times 1 radian per 6 centimeters. Because remember, you multiply by the reciprocal, it's in the denominator. So then we just have to simplify. So your centimeters are going to cancel out, notice, and you're going to be left with a radian per minute, so an angle per time. So 640 divided by 6 is going to give me the 320 pi radians over 3 minutes. And that is my angular speed of the large pulley. So now we've found the angular speed of the small pulley, the large pulley, and of course the linear speed, which was connected by the belt for both of them. All right, so for this next one, it says a circular mobile above a baby's crib makes 5 revolutions per minute. So that 5 revolutions per minute, revolutions per time, so angle versus time is your angular speed. What is the angular speed of the mobile in radians per minute? So for this one, we just need to make a conversion. So angular speed is equal to 5 revolutions per minute times, we know we have 2 pi radians per 1 revolution. So these are going to cancel out to give us 10 pi radians per minute. So that would be the angular speed. So then for the next part for B, it says how fast is the toy 9 inches from the center traveling in feet per minute. So in this case, we have how fast. So this is going to be our linear speed. And remember, the linear speed is equal to r theta over time, which is the angular speed times the radius. So the angular speed is 10 pi radians per minute. Times the radius, which is 9 inches, and we want it in feet, so 9 inches per 1 radian. So to convert to feet, we need to multiply this. There's 1 foot has 12 inches, so that's going to cancel out my inches. So the radians cancel out, the inches cancel out. We're left with feet per minute, which is what we need. So I just got to multiply it straight across for my numerator and my denominator and just simplify it. So when I do that, I get 90 pi feet over 12 minutes, which becomes 15 pi feet per 2 minutes. And that gives me my linear speed. So then the next question is basically the same, except for we're changing it to 6 inches from the center, and again it's feet per minute. So for C, we have the linear speed is equal to, again, the angular speed times the radius. So in this case we have 10 pi radians per minute times 6 inches per 1 radian times 1 foot 12 inches. So notice that your radians cancel out, your inches cancel out, you'll be left with feet per minute. So this is going to give me 60 pi feet over 12 minutes, which is equal to 5 pi feet per minute when we simplify. So that's it for this one. So let's go ahead and look at the next question. The last one. So this is very similar to the first question that we did. So the second hand on the clock is 5 inches long. How far does the tip of the second hand move in 45 seconds? So now, of course, we're starting here and we're moving to 45 seconds. So we need to figure out what that angle is equal to. So we know R is equal to 5 inches. We know that theta is going to be a part of the whole. So 45 out of the 60 gives me part of the whole, which is 3/4 a revolution. So we multiply that to 2 pi, we end up with 3 pi over 2 radians. So for the next part, we need to then just use our formula. Linear speed is equal to the arc length over time. So in this case, we have 5 inches over 1 radian times 3 pi over 2 radians. That's going to cancel out my radians. And our time is, of course, 45 seconds. So all we have to do now is simplify. So this gives us 15 pi over 2 inches divided by 45 seconds. So that means that the tip of the second hand moves 15 pi over 2 inches in 45 seconds, and 15 pi over 2 is actually about 23.56 inches in 45 seconds. And that's the conclusion to our linear and angular velocity. So as we said before, it's really important to make sure you know your formulas for these linear speed and angular velocity. So that would be these two right here. So our linear speed, of course, is our arc length over time, and angular speed is equal to the angle versus time. But like I said, a lot of the times for both of these formulas, I'm going to be using, or you'll probably be using instead, that the linear speed is equal to radius times the angular speed. That's usually the easiest one to use.